Your phone is mid-call when a core network node quietly goes down for maintenance. In older networks, that could mean a dropped call and a storm of re-registrations. In 5G, something different is supposed to happen. The radio access network picks another access and mobility management function, the AMF, and your session keeps going. The AMF is the control plane brain that handles registration, mobility, and connection management for your device, the user equipment or UE. The next generation radio access network, or NG-RAN, is the 5G radio side that must decide which AMF should own that UE's signaling. That decision is called AMF Selection. Get it right, and the network stays resilient under failures, upgrades, and load spikes. Get it wrong, and you risk broken sessions, race conditions, or mass paging storms. In this lecture, we will walk through how NG-RAN and peer functions choose an AMF, how AMF sets and pointers work, what happens for mobile originated and mobile terminated traffic, and how planned maintenance can run with almost no service impact. Think of an AMF set as a team of AMF instances that can all serve the same group of UEs. Instead of pinning every phone to one fragile server, the operator deploys several AMFs that share context through a unified data storage function, the UDSF. Why does that matter in the real world? Imagine a city stadium event. Thousands of phones wake up at once. One AMF would choke. An AMF set spreads the load, and if one instance fails, another can pick up the context from the UDSF. NG-RAN learns about these AMFs when they advertise over the N2 setup interface. Each AMF can advertise a common address for the set and a distinct address for itself. That dual advertising is the foundation of resiliency for UEs returning from idle mode. The radio network already knows who is in the set before the phone even sends a new request. When a UE talks to the network, it often carries a temporary identity, the 5G STMSI, or a globally unique AMF identifier, the GUAMI. Buried inside that identity is an AMF pointer. The pointer is a small routing hint. Pointer value 1 might map only to AMF 1. Pointer 2 maps to AMF 2. Pointer 3 to AMF 3. But pointer 4 can map to every AMF in the set, AMF 1, 2, and 3 together. Here is the part that matters. If the pointer points to more than one AMF, the 5G access network can pick any instance in that group using weight factors. Weights are like traffic lanes. A beefier AMF gets a higher weight and absorbs more UEs. Picture three friends sharing a group chat address and also private numbers. If you only have the group address, any friend can answer. If you have a private number, you reach that specific friend. The NG-RAN uses exactly that idea when it routes the N2 message toward the right AMF instance. AMF selection is not something NG-RAN does on every single message for fun. It kicks in under clear criteria. First, the AMF is unavailable. Either it failed or it is under planned maintenance. The radio access network or another network function may then choose an alternative AMF inside the same set. Second, the UE returns from idle mode, or the N2 transport association is released. The old binding may be gone, so RAN may select an alternative AMF in the set. Third, the AMF itself says it is no longer serving UEs tied to a certain GOAMI. That is a deliberate handoff signal. Pick someone else in the set. A useful analogy is a hospital ward. If your assigned doctor is off shift, on leave, or has transferred your chart, the ward desk does not freeze. It assigns another doctor who can open the same electronic record. The UDSF is that shared chart cabinet for AMF context. Walk through a mobile originated case. The phone starts the signaling. Call this Case 1. The access network reaches an alternative AMF. Step 1. The UE provides its 5G STMSI or GUAMI to the 5G access network. If the AMF pointer maps to more than one AMF, or the preferred AMF is marked unavailable, or the access node detects a failure, the 5G AN can select any AMF instance from the set using weight factors. Step 2. The chosen AMF fetches the UE context from the UDSF. That shared store is what makes the swap possible without the phone redoing a full registration from scratch. Step 3. The new AMF processes the request as if it had always been the serving node. In the diagram, AMF1 is crossed out. Traffic from UEA is steered to AMF2 or 3. The phone may not even notice. That is resiliency for idle to connected transitions done right. Context follows the set, not a single box. Sometimes ng-ran must choose both an AMF set and then a specific AMF inside it. That happens in 3 situations. 1. The UE provides no 5G STMSI and no GOAEP at all. A fresh attach with no routing hint. 2. The UE provides those identities, but the routing info is not sufficient or not usable. Classic example. The GOAEP carries an AMF region ID from a different region, so local RAN cannot honor it. 3. The AMF has told the access node that the GOAEP is unavailable. No target AMF was named, or the access node itself has detected AMF failure. When picking the set, ng-ran may look at AMF region ID and set ID derived from the GOAEP, the requested NSSAI, that is the Network Slice Assistance Information, and local operator policies. Slices matter in real deployments. A ultra-reliable factory slice might land on a different set than a consumer broadband slice. Inside the set, selection weighs availability of candidate AMFs and load balancing across them, again using those weight factors. Availability first, then fairness of load. That ordering keeps failed modes out of the path before you worry about perfect balance. Now flip the direction. A UE terminated request means the network is trying to reach the phone. For example, a downlink data notification from the session management function, the SMF. Case 2. The SMF selects an AMF for mobile terminated traffic. Step 1. A control plane network function such as the SMF is notified that the old AMF is unavailable. The SMF does not give up. It selects any other AMF in the same set. Step 2. That newly chosen AMF retrieves the UE context from the UDSF, becomes the owner, and the path toward the UE can be rebuilt through ng-ran. Real-world picture. You receive an incoming VONR call while the AMF that last saw your phone is mid-restart. The SMF already knows the set. It picks a healthy sibling. Context is loaded from UDSF, and paging or N2 signaling proceeds without forcing every idle UE in the tracking area to re-register at once. Distributed systems create races. Case 3 is the race condition the design must survive. Watch the sequence. The SMF selects AMF3 for the UE. AMF3 retrieves context from the UDSF and marks itself as the owner. Meanwhile, the access network is still unaware of the new owner and independently selects AMF2. AMF2 asks the UDSF for the context. The UDSF rejects that claim and returns the identity of the real owner, AMF3. So AMF2 forwards the request to AMF3. Step 4A closes the loop. Without the UDSF acting as the source of truth for ownership, 2 AMFs could both believe they serve the same UE, and signaling would fork. With it, the latecomer yields and forwards. Think of 2 reception desks grabbing the same patient file. The central record system says who checked it out, and the other desk redirects the visitor. That single rejection plus forward pattern is what keeps mobile terminated and mobile originated paths from corrupting each other during failover. Operators need frequent software upgrades. The source describes AMF planned maintenance, load rebalancing, and auto recovery as a seamless story. No UE interaction and no service impact in idle or connected mode. On the per network function side, peers subscribe for status notifications. When AMF1 goes unavailable, it stores UE context in the UDSF and notifies unavailable status for its GUAMIs toward the RAN, peer NFs such as SMF or UDM in the NRF. Critically, RAN considers AMF1 unavailable but keeps UE context, including NGAP UE IDs, and does not release RRC for connected UEs. Peers keep UE context too. They do not tear down PDU sessions. Later, when an N2 message must be sent for a UE that was served by the old AMF, RAN selects another AMF from the same set. That is a per UE transaction. The new AMF retrieves context with the NGAP UE AMF ID, then notifies peer NFs of the AMF change using the SUPI. The new serving AMF takes over without a mass event. What does the user experience? A voice call is not dropped. A data session stays up. Idle phones are not blasted with mass paging just because an AMF was upgraded. That last point is huge at scale. Mass paging can overload signaling just when you wanted a quiet maintenance window. None of this works if failures stay invisible. The design lists three practical detection paths. First, the RAN or a control plane NF detects that a message cannot be sent after a timeout. That is, after a configured number of retries. Simple, local, and fast for the path that is actually trying to talk. Second, Operations Administration and Maintenance OAM detects the AMF failure, configures the NRF, and the NRF notifies subscribed NFs about the unavailable GOA/GAMs. This is the managed network-wide broadcast of bad news. Third, NF service failure and restart detection using the NRF itself. The repository watches lifecycle, not only static configuration. Together, these cover both data plane silence and operator-driven declaration. Planned maintenance can deliberately mark GWAMs unavailable before the process stops. Hard failures are caught by timeouts and NRF. Either way, selection logic we already covered has clean inputs. This GWAM is gone. Pick another AMF in the set. And the same mechanisms work in deployments with a UDSF and in models without one, though shared context clearly makes takeover smoother when UDSF is present. Pull the thread together. AMF selection is how 5G keeps mobility control alive when individual AMFs fail, overload, or go into maintenance. NG-RAN uses 5G STMSI or GWAMI and the AMF pointer, sometimes aiming at one instance, sometimes at the whole set with weights. When identities are missing, unusable, or the AMF is down, RAN chooses a set using region, set ID, NSSAI, and policy, then an instance using availability and load. For network-triggered traffic, the SMF can pick another AMF in the set and reload context from the UDSF. If RAN and SMF disagree for a moment, the UDSF ownership mark forces a forward to the true owner. Planned maintenance notifies GWAMI unavailability, preserves connected RRC and PDU sessions, avoids mass idle paging, and migrates per UE when the next N2 message arrives. Failures surface through timeouts, OAM, and NRF. The design goal is simple to say and hard to implement. The UE keeps service while the control plane quietly changes hands. That is AMF selection in NG-RAN.